Hi folks, welcome to this recap of functions in Math AASL for the IB course Analysis and Approaches Standard Level. This presentation isn't produced by IBO, nor is it endorsed by IBO. It's just one that I made for my students in PEI Canada to help them before their IB exams. It doesn't have all the topics that are in functions, but it's an overview of the key concepts. There are timestamps and downloadable notes in the video description. I think one great way to get a lot out of this presentation is to pause the video and to try the questions and then check the answers to see if you're on the right track. You can make use of some of YouTube's accessibility options, and please remember that there are often many different ways to solve a particular problem. So if you have a different way, great, keep doing that as long as it's getting you a correct answer. With that out of the way, let's dive in. The big idea of functions is that these are relationships where one variable depends on another. There's only one output value, or y, for each x. Domain is the set of all valid input values, or x values, for a function. We're dealing with real numbers in Math AASL. So here are the things that are going to limit domain. Division by 0. If you have 1 over something, that something cannot be 0. Even roots of negatives. If you have, say, the square root of something, then that something has to be greater than or equal to 0. Logs of 0 and negatives. So if you have the log of any base of something, then that something has to be positive. And lastly, certain values of tan, where you're going to have asymptotes, so that would be at pi over 2 and 3 pi over 2, etc. And this one is really just the same as condition number 1, division by 0, because tan is sine over cosine. But we're going to really just focus in on the first three. Range is the corresponding set of output values, or y values, in a function. To find that, the graph, or knowledge of the asymptotes, maxima, minima, is all going to help. Composite functions are functions that have an inner and an outer part. When you see this notation, f composed of g of x, it means f following g of x, or think of it this way, f of g of x. When you evaluate, start from the inside. In general, order matters in function composition, so f of g of x tends to be different than g of f of x. Inverses. F inverse of x is not just 1 over f of x. The inverse is the undoing of f. So if f was add 3 to a number, the inverse would be subtract 3 from that number. Inverse sine is a good example of an inverse. When you take the sine of an angle, you find a ratio of sides. When you do inverse sine of some sort of ratio, then it gets you back to the angle. We find the inverse by switching x and y. And graphically, inverses are reflections of each other through the line y equals x. And y equals x looks just like this, 45-degree line. The identity function, y equals x, is one where the input equals the output. And again, that's that 45-degree line. A property of composition of inverses is that f of the inverse of x, and doing it the other way around, just gets you back to x. Intuitively, the f is doing something to x. The inverse is undoing that thing. And if you do both of those in either order, you'll just get back where you started. It's the same thing as adding 3 to a number, then subtracting 3 from a number. Gets you back where you started. With those definitions out of the way, let's try just evaluating some functions. So here I've got f of x, g of x, and h of x. And we want to find g of 5 over 2, or g at 5 over 2, if you want to say it that way. So that would be 4 to the 5 over 2. I just put in 5 over 2 for x in g. And 5 over 2 as an exponent means the square root of 4 raised to the power of 5, or 2 to the 5, which is 32. H of g of negative 2 means just like this, h of g of negative 2. So what we're going to do first is find g of negative 2. And maybe I'll even do that off to the side. G of negative 2 would be 4 to the negative 2, which is 1 over 4 squared, or 1 over 16. So this function is secretly asking us, when it says h of g of negative 2, what is h of 1 over 16? Okay, because that's what g of negative 2 was. And then we sub in 1/16 into that h function. So we'd have 1/16 squared minus 1. That gives us 1 over 256. We're going to subtract some fractions, so we need a common denominator. And work that through, we'd get negative 255 over 256. The next question is asking us to find the inverse. So to do that, we switch x and y. F of x really meant y equals 2x minus 3. So the inverse is going to be x equals 2y minus 3. And now all we do is isolate y. So that would be x plus 3 equals 2y, or y equals x plus 3 over 2. Or if we write it with the nice notation, that would be f inverse is x plus 3 over 2. So just for clarity here, the original function, 2x minus 3, would have looked something like this. Its inverse would be a reflection through the diagonal line. It will look something like this. We'll look more at inverses later on in the presentation. H of x equals 0. We're going to solve this for x. So here, we're not putting in 0 for x. We're putting in 0 for h of x. So we have this little equation. 0 equals x squared minus 1, or 1 equals x squared. When you square root both sides in an equation, you need to consider either the positive or the negative possibility. So there are two answers here, x equals 1 and x equals negative 1. Another way that we could have done this is by factoring, since we had a difference of squares, and that might make it easier to find those answers. X is negative 1, and x is 1. Okay, harder to miss the two possibilities when we factor. In terms of GDC skills, we need to be able to accurately produce a graph from the GDC, show domain and range, any max or min, asymptotes and turning points. You also need to be able to solve equations graphically. We'll deal with those concepts in this video, but also there's a GDC skills video that you can check out. This all leads us to looking at lines, or linear functions. So three common forms that you'd see lines written in, or equations given for them, are slope and y-intercept form, or you might know it as gradient and y-intercept. Y equals mx plus whatever letter you want. It's C in the formula booklet. General form is when you have 0 on one side. And then point slope form, y minus y1 equals mx minus x1. Slope and y-intercept form is great for graphing and for putting into a GDC, since we need to put things in y equals form. Point slope form is excellent for finding the equation of a line. Now, to use point slope formula to find the equation of a line, you have to know two things. Can you guess what they are? That's right. You have to know point and slope. Speaking of slope, or gradient, sometimes it's just called rise over run, but m represents slope here. Change in y over change in x, or y2 minus y1 over x2 minus x1. To graph a line, there are a lot of ways to do it, but basically what you need is 2 points and a straight edge. So let's take a look at a couple of questions here. If we want to draw the line y equals 3x minus 4, which would normally have an unrestricted domain, but here they're saying only from 0 to 5. And this is a classic IB sneaky move, is to ask you to graph it for a particular domain, and then give you more than that domain in the graph. So notice that this grid goes from -1 to 6 on x, but we're only supposed to graph it from 0 to 5. If you want, you can use the y-intercept and slope. What I'm going to do is just make a little table of values. And I'm going to use the starting and ending points, though I could use any points at all. So if I put 0 in for x, I'd have 3 times 0 minus 4, or -4 for y. Great, that's a point. If I want to put in 5 for x, well, that would be 3 times 5 minus 4, or 11. So there's another point, 5, 11. And all I need is a straight line connecting those. I take out my ruler, and here we go. Not the only way that you could get the graph of this line, but certainly a way that works. The next question asks us to find the equation of the line that passes through these 2 points. And finding the equation of a line is probably something that will come up in tangents in calculus, as well as maybe for more basic questions like this one. So I need to know a point to use this point-slope form. And so I know x1, y1. That's great. Here's x2, y2. I also need to know the slope, which is y2 minus y1 all over x2 minus x1. That's going to give me -8/3. And if I had switched the order of those points and made the first one x2, y2, I'd still get the same result. So now I use this point-slope form to find the equation. So y minus y1, so that's a 3. M, slope we just found, is -8/3. And we'd have x minus x1, so minus -1. Minus a -1 is probably better expressed just as x plus 1. And that's the answer if we are not asked for a specific form. Now, often we'll want it in y equals form when we're done, so let's just work it through. -8/3 x minus 8/3. I'm going to have to add 3 to both sides. And 3 is 9/3. So in the end, we'll have something like this. Y equals -8/3 x plus 1/3. And there we go. There's an equation for a line that passes through those 2 points. If you want, you could check it in your GDC and make sure that it actually goes through those 2 points. This leads us into considering parabolas. But before we get into quadratic functions or parabolas, just a couple of general ideas here. If you want to find the y-intercept of a function, as long as it has one, then just sub 0 for x. If you want to find the x-intercepts, if any, then you sub 0 for y. That makes sense because the definition of a y-intercept is a place where x is 0, and the definition of x-intercepts are places where y is 0. Quadratic functions. These are polynomials where the highest power is x squared. So linears have the highest power of just x to the 1. Quadratic graphs are parabolas, and there are 3 common forms to write them in. So parabola is kind of a U-shaped thing. Vertex form is super helpful. All these letters are arbitrary. Maybe you'll use different ones on the exam. Maybe you use different ones in class. But vertex form is a times x minus something, all squared, plus k. What we like about this form is that it tells us the vertex, which is this kind of spot on the graph. The vertex is at hk. So, for example, if I were to write -3x minus 1 all squared plus 5, the vertex on that graph would be at 1, 5. If it had been x plus 1, then the vertex would be at -1, 5. The x-coordinate of the vertex also tells us the axis of symmetry, which is the vertical line that splits the parabola in 2 symmetrical parts. The a value determines the direction of opening and steepness. So on this particular function, we'd be opening downwards, and it would be pretty steep. So it would be a parabola that looks something like this. I don't know where exactly all those axis intercepts are, but I do know that the vertex would be at -1, 5. It would be opening downward and relatively steep. The next common form that we're likely to see is factored form. So this is a times 2 binomials multiplied together. And in this case, we learn the x-intercepts. So if you had something like this, y equals 1/2 x minus 3, x minus 7. That would have x-intercepts at 3 and 7. Honestly, I just think of them as the numbers that zero out each of those brackets. This particular one that I wrote here is going to be opening upward, and it's not going to be that steep because it has a half in front. On a graph like this, the vertex and the axis of symmetry have to lie halfway in between those x-intercepts. So if I show it something like this, the axis of symmetry would have to be at 5. X equals 5. And the vertex is going to be at 5 something or other. Now, I can find what value that is by subbing in 5 into the equation. I don't want to get too far into it, though, because we have some examples coming up. The a value determines the direction of opening and steepness, so it opens upward because it's positive 1/2. But not every parabola can be expressed in this form, and that is because not every parabola has x-intercepts. It's possible to have a parabola that exists entirely above the x-axis or entirely below the x-axis. That leads us to a third form in which you might see a parabola presented to you. That's trinomial or expanded form. And this one isn't good for a whole lot. C is the y-intercept, because if you put 0 in for x, that's all you'll be left with. A still determines the direction of opening and steepness, but those key features like x-intercepts and the location of the vertex are not known to us. Now, one thing that is known is that the axis of symmetry is negative b all over 2a. That is also the x-coordinate of the vertex. Often, if we want to understand a graph that's presented in this form, we want to convert it to a different form, probably vertex form. And it can be converted to vertex form through completing the square, through using the axis of symmetry, or using differentiation techniques. So that's exactly what we're going to do. We're going to take a quadratic that's in trinomial form, and we'll convert it into vertex form. You can do it a bunch of ways, and I'm going to go through 3 ways here. But before we do any analytic ways, I'm just going to use my GDC. There's the equation. I hit graph. I can find the vertex by going second calc max. And I have to give it a left bound and a right bound. This may be a little bit different on your GDC. It tells me that the max is at 1.5, negative 6.5. So I actually know from that that the answer is going to be y equals negative 2 and the coordinates of the vertex, 1.5, 6.5. On paper 2, this is probably a 2-mark question. On paper 1, maybe a little bit more. So let's go through these 3 techniques, though you only need to be able to do really one of them. You can take whichever one you find most comfortable. I'm going to take this negative 2 out as a common factor. I'm only going to take it out of the first 2 terms, though different people do it differently. And here's what I do. I take half of the middle term, so that would be negative 3 over 2, and I square it. That is the magic number that I'm going to both add and subtract. So that keeps it balanced. After I do that, these first 3 terms over here form a perfect square trinomial. So it's going to be x minus 3 over 2 all squared. And then I'd have minus 9/4 minus 11. I can multiply out, and I'll get negative 2 x minus 3 over 2 all squared minus 9 halves, sorry, plus 9 halves minus 11. And I just work this through. Negative 2 x minus 3 over 2 all squared, and that would be plus 9 over 2 minus 22 over 2, negative 2 x minus 3 over 2 all squared, minus 13 over 2, which is the exact same as this answer over here. I find that often students find this a painful way of doing it, so another way that you could approach it is by using the axis of symmetry. And really, in this case, we're just looking for the x-coordinate and y-coordinate of the vertex. Well, the x-coordinate is going to be wherever the axis of symmetry is, which is negative b, so that'll be negative 6 over 2a, and that's in your formula booklet. That would be negative 6 over negative 4, or 3 over 2. Great. The y-coordinate would come from just subbing in 3 over 2 for x. And I'm just subbing it in to the y equals equation over here. So that would give me negative 2 times 9/4 plus 9 minus 11, or negative 9 halves plus 9 minus 11, or just minus 2, or y equals negative 13 over 2. Once I know where the vertex is, I know that in vertex form, this is going to look like this. X minus 3 over 2 all squared minus 13 over 2. Same answer, different approach. Lastly, we could do this by thinking about the first derivative. The tangent slope of y is going to be y prime, and that's negative 4x plus 6. If we're looking for a turning point, well, we set the slope to be 0. So we get negative 4x plus 6 equals 0, or 4x equals 6, or x equals 3 over 2. That's where we're going to be turning around on the graph, and we can similarly find out that the y value is negative 13 over 2 using the same technique that we did over here. That's going to let us know that the vertex is this, and the result is the exact same. You can use whatever technique you want, but make sure that you're conversant in at least one of these. In that last one, when we got it in vertex form, we probably could have graphed it. In this question, we're going to be given a graph and some information, and be asked to find the equation. So the graph alongside is a parabola with x-intercepts at negative 1 and 5. Its equation could be written in this form: a, x minus m, x minus n, where m is less than n. So let's think about that. I think a lot of people will get this right and think, oh, that means it's got x-intercepts at negative 1 and 5, so it's going to be an x plus 1 and an x minus 5, because negative 1 would zero out the first bracket, and 5 would zero out the second bracket. That means that the answer to this question is m equals negative 1 and n equals 5. And I can already feel the jackals of the internet writing in saying, no, it's not, it's m equals 1. So let's just go through the form here and just make sure we're clear on how this is all working, because the IB loves to set these things up, so it takes a little bit of extra thought. They've given it to you as x minus m, so that x plus 1 is actually x minus negative 1. And this one here is x minus 5. So what is m? M is this, negative 1. What is n? N is this, 5. Okay, there's a minimum at p negative 36. Find the value of p. So let's see. That means this point right here, p negative 36. Let's actually just asking for the x-coordinate of the vertex. And we know that that should be halfway between negative 1 and 5. Now, a lot of people will be able to just intuitively say that halfway between negative 1 and 5 is at 2. But if you're ever looking for a halfway point, the easiest way is just to add up your numbers and divide by 2. You're really finding an average. So p equals 2. Hence, write the equation of the parabola. So using that fact, here's what we know at this point. Y is a times x plus 1, x minus 5. This is the way I'm going to do it, but you could maybe do it a different way using a different form. What I don't like about this equation is too many letters. I just got an a, an x, and a y. I really need to know the value of a. But thankfully, I now know that there's a point on this parabola of 2, negative 36. So let me sub that in. It is a special point, but it's a point nonetheless. Y is negative 36 when x is 2. And from there, we can just solve. That is a times 3 times negative 3, or negative 9a is negative 36, or a is 4. So whereas we knew before that the equation is a by x plus 1, x minus 5, now we know that a value is 4. And I have to write it in this trinomial form. I probably have most of my marks even without doing that. I'm going to FOIL out these brackets, or distribute. So x squared minus 5x plus 1x is minus 4x minus 5. And then I'll distribute in. Okay, I'm not going to double multiply by accident at the start. So we get 4x squared minus 16x minus 20. That takes us through some graphical stuff. Now let's look at some single variable equations. When you're solving a regular linear equation, you just put your variables on one side and your numbers on the other, and you're done. When you're solving a quadratic equation, things can get a little bit trickier. But what helps us out is this zero product principle that says if a times b is 0, then at least one of those two things is 0. If we want to solve quadratic equations, what we'll do, as long as it's not too rough, is make one side 0, factor, and then solve the elementary equations that ensue. Now, I'm not going to go through how to factor in this video, but there are tons of great tutorials on the internet about that. In particular, I think Nancy Pye's factoring videos are excellent, formerly Math BFF. So if I've got this equation down here, mercifully, it's already equal to 0. I'm just going to factor it. I'm looking for firsts that multiply to 2x squared, so that would be 2x by x. And then I got to put a 5 and a 1 somehow in here. Let's see. Yeah, this is going to work out. I could multiply it out, make sure it's correct. And then each bracket gives me an elementary equation. If the first bracket is 0, then the equation is balanced. If the second bracket is 0, the equation is also balanced. So I can just go through and solve each of these elementary equations. X is 5 over 2, or x is negative 1. I guarantee you, if you put either of those back in the original equation, you'll get a balanced equation. It'll say 0 equals 0. Quadratic inequalities are also in the syllabus. So you can solve them close to the same way. We could factor here. And here, that would be greater than 0. So we're wondering, where is this greater than 0? There are a few ways to deal with quadratic inequalities. One way is to think, well, what are the solutions to the equation? Negative 1 and 5 over 2. Those would be x-intercepts on the graph of this function. Okay, if we thought about the basic look at this function, it's a parabola that opens upward. Looks something like this. So where is it greater than or equal to 0? Well, it's greater than or equal to 0 on this region right here, which is where x is less than or equal to negative 1, and also on this region over here, or where x is greater than or equal to 5 over 2. Another way that people sometimes like to do it is they'll choose a number less than negative 1 and they'll sub it in. So if I put in, say, negative 2 into this function, I'd have 2 times negative 2 minus 5. I'd have a negative from this bracket. I'd also have a negative from this bracket. That would give me a positive, which is greater than 0. So this area would satisfy the inequality. If I put in something between negative 1 and 5 over 2, say 0, in for this bracket and this bracket. So let's say I put in 0. This one would be negative, this would be positive. The whole thing would be negative, and that would not be greater than 0. So this would not work. And if I put in something bigger than 5 over 2 in here, I'd get a positive times a positive. Oh yeah, it would be positive, so that would check out. I kind of like the graphical approach, or just an informal approach is fine too. But you may end up with quadratic inequalities, particularly when we're looking at sign diagrams for the first derivative. However, being able to solve a quadratic equation is way more important than an inequality. Alternately, if we can't factor, or if it's difficult to factor, we can use the quadratic formula, or if it's paper 2, just our GDC to solve. If you're solving the equation graphically on your GDC, there's no need to rearrange it. So this one over here, x squared plus 1 over x plus 1 equals 3. If I want to solve it graphically, I will put in one side of the equation as one function, and I'll put in the other side of the equation as a different function. I'm going to go to standard window settings, and I'm just going to look for the points of intersection. Any x values of intersection are solutions. So I go second, trace, down to intersect. I go a little bit to the left of the first intersection, and then a little bit to the right. And it may be hard to see there, but in purple it's telling me that x is equal to negative 0.562. I press second trace, do the same thing, and hunt down that other intersection. I go a little to the left, a little to the right. This may be a little bit different on your calculator because I'm on an emulator, but we get 3.56. We want to be able to solve equations graphically because on paper 2, there's no point in wasting our time doing an analytical technique when we don't have to. On the other hand, if we don't have our GDC, well, then we have to find some way to deal with this. And you might look at it and say, that doesn't look like a quadratic. But the first thing we might notice is it's got a fraction. So let's try and get rid of the fractions. We'll multiply both sides by x plus 1. That'll give us x squared plus 1 equals 3x plus 3. Ooh, that's starting to look like a quadratic. Let's move that 3x over. I'm going to move the 3 over as well. And there's a quadratic in equals 0 form. And it's not one that factors very well. You've got to look for numbers that add to negative 3, multiply to negative 2. They exist, but they're not rational numbers. So that's going to lead us to the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And then we sub in. So b is this negative 3, so negative b would be positive 3. B squared would be negative 3 squared, so that's 9. Minus 4 times a would be the coefficient of x squared, so that's just 1. And c is negative 2. And again, all over 2a. So 2 times 1. And then I just work it out. That's 3 plus or minus the square root of, let's see, 9 plus 8, so that's 17, all over 2. It's important to realize that this actually represents two different numbers, 3 plus root 17 over 2, and 3 minus root 17 over 2. Now, if you found decimal approximations of those, guess what? They're negative 0.562 and 3.56. You may also run into even sneakier quadratics, like these exponential ones here. This is really e to the 2x, so that's e to the x all squared, minus 2 equals e to the x. That's really fishy. I could rearrange that as e to the x squared minus e to the x minus 2. That looks a lot like something like n squared minus n minus 2. And this would be equal to 0. And we'd try to factor if we can. I mean, we could use quadratic formula, but that's kind of a pain. And this factors really nicely. If it were in n's, it would factor to n minus 2, n plus 1. Here, the only thing that's different is that it's e to the x's. So this would be e to the x minus 2 and e to the x plus 1. Those give elementary equations for us to solve. So the solutions are either where the first bracket is 0 or the second bracket is 0. So that would be e to the x equals 2. You could take the natural log of each side, or you could change forms if you want. You can use the power law of logarithms, and if you haven't done logs yet, then obviously don't worry about this. But this presentation is kind of intended for the end of the course, so hopefully at the end of the course you have seen some logs. So x could be ln 2, and this would give us e to the x equals negative 1. Keen eyes at this point will say, oh, that's not possible. And if I take the log of both sides, that would be ln e to the x equals ln of negative 1, which is not a thing in the real number system. So this part doesn't give you anything. So no solution from that part, but this part is good. Our final answer is x equals ln 2. So a sneaky quadratic in that case. The discriminant is just the part under the square root in the quadratic formula. So I have math socks that give the quadratic formula just like this. Negative b plus or minus the square root of the discriminant over 2a. And if the discriminant's negative, then there are no real solutions. If the discriminant's 0, then you can have negative b plus or minus 0. So that's just 1. You can think of it as repeated x-intercept, a real solution. On a graph, that means the vertex is going to be on the x-axis. And if the discriminant is positive, well, then you have negative b plus or minus a number. So you have two distinct or different x-intercepts or real solutions. The discriminant tells us how many x-intercepts or how many real solutions exist. Anytime you see a question that asks you how many solutions there are, particularly if there's a quadratic involved, that's a discriminant question. It's very unlikely that the question's just going to ask you to solve a quadratic, but first find the discriminant. Often it's going to be to use the discriminant in kind of an analytic way. So here's an example question. The function f of x is x squared minus 5x plus 2k, and it has no x-intercepts. Super fishy. No x-intercepts means we're talking about the discriminant. And the discriminant is less than 0. Okay? It's negative if there are no x-intercepts. B squared minus 4ac is the discriminant. It says find all possible values of k. So b squared, that would be negative 5 all squared minus 4 times. A is 1. And c is this value right here, 2k. So it's fishy also because it has an extra variable in there. So 25 minus 8k is less than 0, or negative 8k is less than negative 25. Divide by negative 8. And in an inequality, if you multiply or divide by a negative number on both sides, then the direction of the inequality changes. So we get k is greater than 25 over 8. If you really want to play it safe, I guess you can do something like this. Move the 8k to the other side, and then do this, 25 over 8. But in terms of syntax, we really prefer to put the variable first. The last topic that we'll deal with in this part of the video is points of intersection. So if you want to find where two functions meet, you can just use the GDC, or you can use analytic techniques. You can equate the functions. So let's do this one analytically, and then we'll go and use the GDC. If I want to find the points of intersection, I set these two equations equal to each other. Oh my gosh, that's a quadratic equation, so I'll make one side equal to 0. I'll factor it because this is easily factorable. If I couldn't factor it, I'd use the quadratic formula. I'll solve the ensuing elementary equations. And that's going to give me x equals 3 and x equals 1. That means that there are points of intersection at 1 something and at 3 something. Now, if I want to find the y value, I just have to sub that 1 back into really either one of these functions. I think it's easier to do it in g. g of 1 is 4 times 1, or just 4. Though it's not like it was harder to do it in f. f of 1 would be 1 squared plus 3, also 4. So they intersect when x is 1 and y is 4. And similarly, when x is 3. And let's see, when x is 3, y would be 12 from either function. Those, allegedly, are our points of intersection. Let's check it on the GDC. I put in both functions. I go zoom 6 for standard window settings. And I go second calc intersect. I go a little to the left of the intersection, little to the right, and it tells me in purple there that it's where x is 1 and y is 4. If I did it for the other point of intersection, it would tell me 312. That brings us to the end of this video. In the next functions video, we'll deal with the other topics that come up in the IB Math AA SL course in the functions section. In particular, that would be general transformation techniques, reciprocal and rational functions, and also logarithmic and exponential functions. I hope that you found this video helpful. Good luck with the material, and take care, folks.